So, Roy kicks a ball. The diagram below shows the trajectory of the ball, so the motion of the ball. You may assume air resistance is negligible. Okay, that's quite a good assumption. So let's underline that. Assume air resistance is negligible, so not really occurring. Okay. On the diagram, draw labelled arrows of appropriate length. So this is really important, and we're going to show the following. The force on the ball at position C and position G. Okay, so they're roughly equal heights at opposite sort of sides of our maximum height. Okay, so we're going to have FG here, and then at G it should be about the same length, and FG. The gravity force is going to be the same no matter where our ball is in its motion, okay? And once the ball has been kicked, gravity is the only external force that is acting. Okay, so that's bullet point 1. Cool. So we've done our first bit, we've labelled the forces. Let's have a look at this horizontal component of the velocity. Okay, at position B and H, so these two here. Alright, now they're roughly the same height off the ground, just on opposite sides of the maximum, like we did for this previous one. So, horizontal velocity. That stays constant once the ball has been kicked, because there are no external forces in the horizontal component. Okay, so we need to draw and label these two being the same size and labelling them with something like VH for horizontal velocity. Okay, now the vertical component of the velocity of the ball at position D and F. So here's D and F, again, same heights, just opposite sides of our maximum. So our arrow for D should be relatively small because we've got near to the top of our curve, pointing upwards, because it is still going up at this point. Now our arrow at F should be about the same, but in the opposite direction, because we're now going down. Okay, and it hasn't had time to build up a lot of velocity. Okay, so same size, opposite directions this time. Okay, so let's label that with VV and VV. Alright, so we've done those three. Okay, let's have a look at the next question. B. The ball is kicked with an initial velocity of 16 meters a second at an angle of 42 degrees. Calculate the initial horizontal and vertical components of the velocity. Okay, so that means that we've got two steps. We've got vertical and horizontal components. Alright, so we're needing to calculate this arrow and this arrow. Okay, let's start with horizontal because we've got horizontal there. So, velocity of the horizontal. Okay, let's look at which components of our right-angled triangle we have for use in trigonometry. So we have the hypotenuse, that's our 16. We're wanting to find out the adjacent, right? So we're going to use cos. Okay, so we need to do 16 cos 42. Okay, making sure to check that your calculator is in degrees and not radians. So we should get an answer of 11.89 meters per second. Okay, and then we need to round that up to 12 meters a second. Two significant figures because we've got 2 here and 2 here. Alright, the vertical component now. So this time we're looking at the horizontal and the opposite. Okay, so when we're using horizontal and hypotenuse and opposite, we need to use sine. So 16 sine 42 is going to give us 10.71 meters per second. Okay, and of course to two significant figures, that's 11 metres per second. Okay, so calculate the initial horizontal here and vertical components of velocity at point A. State the horizontal and vertical components of the velocity at point E. So here is point E, we're at the top now. Explain your answers. Because it's a state, we don't have to do any more calculations, okay? We should be using information we've already got and some prior knowledge. So, let's look at the horizontal component first. So at part E, what is the horizontal component? Okay. Horizontal velocity at E will be this value here, 11.89 meters per second, as this stays constant throughout the projectile motion, as there are no external forces. Okay. The vertical velocity will be 0 meters per second. Okay. As it is at the top. And gravity acts vertically downwards decelerating the ball until the peak, which is 0 meters per second. Okay, so we need to talk about horizontal and vertical components. We need to specifically state a number. Okay, and then we need to explain why they are those numbers. Okay, so for horizontal velocity, we've got no external forces in the horizontal direction, so we get this constant velocity from start to finish. In the vertical, alright, we have gravity acting in the downwards direction, so as we go up towards the maximum, that gravity, remember it's an acceleration, it's in meters per second squared. Okay, as we go up, it reduces and reduces the vertical velocity until we get to 0. Alright, and that is our peak height. And then that force accelerates, decreases and decreases because now it's in the same direction as our vertical velocity. And so we get faster and faster towards here. Okay. Calculate the horizontal distance the ball travels before returning to the level from which it was kicked. Okay, so this is looking like a two-step process. Okay, the first step is to calculate time to top. Okay, so that's going to give us the time from when it was kicked to the top of the curve. Alright, so what information do we have? We have VI, we have VF, we have an A, and we're wanting a T. Okay, So our VI, at the moment we're actually going to work in the vertical, not the horizontal, okay? So we're going to calculate the time to the top, so we're working in the vertical, the up and downs, okay? So our VI is our vertical velocity that we calculated on the previous page, okay? And we're going to use the unrounded value, so 10.71 meters per second, okay? Our VF, once we reach the top, is 0, as we stated in the previous question, okay? Our acceleration, because we're working in the vertical, is 9.8 meters per second, and we're wanting to work out the time, okay? So when we have a look at the resource sheet, we find that our equation VF equals VI plus AT. Okay, so let's rearrange that to find T. So VF minus VI equals AT. VF minus VI divided by A equals T. So then we just need to substitute our values in. T equals 0 minus 10.71 divided by negative 9.8 because we're going to show direction. So what we should get is a time to get to the top of 1.09 seconds. Okay. Step 2. Calculate total time. Okay, so this is pretty easy. If we've got time from kick to the top, then time from kick to the top to back to the bottom is going to be twice this. So 2 times 1.09 equals 2.18 seconds. Okay, that's pretty straightforward. Then we need to calculate the horizontal distance. We're actually getting to answer the question. Okay, so because it's horizontal distance and because we have no external forces acting, alright, we don't need to use one of the fancy kinematic equations. We can just use our velocity equation from year 11. Okay, we are going to have to rearrange it, but that's the one we can use. Okay, so we need to rearrange it, so we're going to get change in distance equals velocity times change in time. Okay, now this velocity is not going to be the 10.71 because that 10.71 is the vertical component. We now need the horizontal component. So that's going to be 11.89 from the previous question. Okay, then we just need to times it by our total flight time, 2.18, and we should get a total distance of 25.97 meters, or when we round up to two significant figures, we're going to get 20 meters. Okay, so because this is a multi-step process, see 1, 2, 3, we're looking at an excellent question here. Okay, so if we end up with this correct time here, we're getting an achieved. If we get to this step, then we're getting to a merit, and if we get through all three, we're getting to an X.